Hello rocket fans! Every time we show a picture or a clip of our DIY space capsule, we get the same question. Does the astronaut really have to sit like that? And honestly, yes. We wish the answer were different, but physics really doesn't care about human knees. So let's talk about why. If we could, we would absolutely love to give the astronaut another 10 centimeters of leg room. We would love to make the capsule more spacious, more ergonomic, maybe even a bit less like a Ryanair seat on a Friday afternoon. But unlike Ryanair, we are not doing it to save money. Our problem isn't money, or well, it is to a certain extent. Our problem is physics. Comfort is in a comfort fight with aerodynamics, and aerodynamics always wins. That's the situation. So even a tiny increase in width will make the rocket dramatically harder to push through the air. If you add 10 centimeters, drag will increase by 21%. Add 20 centimeters, and you're looking at roughly 44% more drag. That's a huge penalty for something that barely helps the astronaut stretch their legs. So before we can talk about comfort or posture or leg room, we have to answer the real question. How wide can the rocket be and still reach space? So here's a simple version. The wider the rocket gets, the more air it has to shove out of the way. And the resistance, the drag, that grows much faster than people expect. Just 1% wider, roughly 2% more drag. Make the capsule half a meter wider, up to 1.5 meters, and you'd get more than double the drag. If you double the width of the rocket entirely, up to 2 meters, and you will get 4 times the drag. No rocket with our engines can survive that. And that's even before we talk about gravity. Gravity is always pulling down, and that never takes a break. So even as the rocket burns fuel and gets lighter, gravity still eats a big chunk of our thrust. So whatever is left has to fight the air, especially in a zone between about 6 and 10 kilometers altitude. If you've ever followed a launch, you've heard the term max Q, the point where drag is at its worst. That's our drag wall. So if you're going to lose the battle against physics, this is where it happens. And this is exactly where diameter matters the most. So if we made the capsule even a bit wider, just 10 centimeters, 20 centimeters, the rocket would hit the drag wall with no power to spare. It would slow down instead of speeding up. And rockets that slow down, they don't go to space. So with our engine setup, there is a hard upper limit to how wide the rocket can be. And that limit is roughly 1 meter. We hear this a lot. Surely 25 centimeters can't hurt a lot. It hurts a lot. Adding 25 centimeters just doesn't make the capsule roomier. It makes the rocket so much harder to push through the air that the engines simply can't cope. The climb stalls, the rocket never gets through the drag wall, and the whole mission becomes impossible. To make it work, we would need it to have bigger engines, more fuel, bigger tanks, stronger structure, basically an entirely new rocket. That's not an upgrade. That's a different project. So even though we cannot change the diameter, we can make the ride as safe and comfortable and tolerable as possible. We've done that by building a semi-reclined seating position, a spring and damping system under the seat, vibration control, and we've made the parachute sequence in such a way that it tips the capsule into the water gently. We also test with crash test dummies, consult medical experts, and we tweak the design constantly whenever we get a new idea. It will never be spacious, but it will be safe enough. So yes, the capsule is small. Smaller than we would like. Smaller than your knees would like. Definitely smaller than what Ryanair would call comfortable. But that size is the only way this rocket can reach space with the engines and the resources we have. So this isn't about building the most comfortable capsule. It's about building the only capsule a volunteer-driven group can realistically launch.